We've now seen a procedure for solving non-homogeneous differential equations where the solution is made up of two different components, one from the homogeneous complementary part and one dealing with the non-homogeneous aspect of the differential equation. To hopefully deepen that understanding a bit, let's look at some application areas. Our first example is going to be our spring mass system again. What we're going to do is write out the differential equation, which came from F equals ma, my double prime, plus a damping thing that had to do with the velocity, plus a constant from the spring times position. And what we're going to do is add an external force. So if you think of these forces here as the damping and the spring, and this is our ma, well, if we had another force, we wouldn't put it on this side unless it had y's in it. Instead, we're going to put it on the right-hand side over here. That is where any other remaining forces would appear. Now, what does this correspond to? Well, imagine this poor mass just sitting innocently by itself at equilibrium, nothing much happening, and then someone came along and pushed on it. And didn't just push once, but pushed and then pulled, and then pushed and then pulled, and then pushed and then pulled. We're going to explore what happens when you do that to a mass system when we have either different amplitudes or different frequencies of that stimulation. Now, a new application we haven't considered is electronics. I'm going to draw a simple circuit here, and you don't have to know electronics to appreciate this, though it certainly helps. And what we have in this circuit are a number of different components. So we've got ourselves a switch here. That's what activates the circuit and completes it. We have a resistor here, and we have an inductor here. People might be less familiar with that. And we have a capacitor down here. This E here is the voltage source. So that's the electromotive force, or the voltage, is going to come in here, and say that's the positive side of it in our diagram. So what happens when we close the switch is if there is some electronic voltage or electromotive force, it'll drive current to run around the circuit. We'll get a drop of voltage across the resistor. The inductor has the same kind of property as does the capacitor, but it turns out they're a little more complicated. At the end of the day, though, we can apply Kirchhoff's laws for voltage drop around the circuit, and what it'll tell us is that the jump across the force side is going to equal the current times the resistance for the resistor. Interestingly, the current, let's make a note here, I is equal to current. The rate of change of the current times the inductor, whose size is characterized by L, the drop of voltage across there depends on how quickly the current is changing and not so much about what its level is. So that's an interesting change. And we also have the capacitor, 1 over the capacitance times something called Q, which is the charge on the capacitor. Now this looks kind of like a differential equation because we have a derivative, but we have a few too many variables. Let's focus first, though, on what we want to know. What we'd want to know is I equals. Current is the unknown. These other elements here are L and C are constants. So how does that help? Well, the interesting thing is the amount of charge that ends up on the capacitor. If we ask how much does that change over time, well, that's exactly what current is. So what we end up doing, if we want to get something like we've seen before, is we take a time derivative of this entire equation. That gives us E prime equals I prime R, just a constant times I, so we take the derivative, just the I part. We get an I double prime times L plus a 1 over C times I, because the derivative of Q is I, and we can put that in standard form quite easily. Li double prime plus Ri prime plus 1 over C times I equals E prime. But we had E of t here given to us, and E prime would simply equal, derivative of cos is negative sine, we get a b popping out, so we would have a sine of bt. Li double prime plus Ri prime plus 1 over Ci equals A sine bt. Now again, you don't need to be an expert in electronics or know how to derive this. Just be able to look at this and go, okay, when we look at circuits, this is the math that comes out, and that math is identical to the mathematics you get, the differential equation you get when you look at a spring system. What's the translation? Well, we have mass, damping, and spring. The inductance, the resistance is like the drag, which makes sense. Resistors bleed off energy. They get hot when circuits are on. They diffuse energy, so they play the role of the dampener. And the capacitor has something to do with the spring. The idea is you charge it up and then it can unspring or discharge back in the opposite direction. It plays the role of the spring force. So there's lovely, lovely parallels with all of this. And you might wonder, well, where would we get a voltage like this coming in that has this strange sine BT form? Well, this is exactly what radio waves do. If you have an antenna and a radio wave is coming into that antenna, you get a voltage across that antenna that drives the circuit, and it'll be some kind of oscillating input function. Additionally, you might also have just a simple AC circuit at 120 Hertz. That might be something else. In other words, there's lots of ways you could get an oscillatory input to this system. The key message again is not that circuits get differential equations, though they do. The more important thing is that they get differential equations that are identical to the spring and mass system. So when we talk about springs and masses, we're not just talking about springs and masses. We could potentially be talking about current in circuits. There are also some other tie-in applications that also have the same structure. We're talking about all of those when we talk about solving differential equations like this.